Okay, so in the last video we talked about leakage current, right, or the ground current, which might flow through the panels, right, to the earth, and then comes or rather closes the path through the substation transformer, and then through the inductor of the through the filters of the inverter, followed by the inverter, right? So that's how it closes the path. So one of the things that we assumed while discussing about these leakage currents was the voltage that appears across the parasitic capacitors, right, of solar panel. So we said that across the parasitic capacitor there is a high frequency voltage which appears, which forces a high frequency current to flow through the panels. Let me just draw it again in case you don't recall. So this was the multiple panels connected in series and parallel, and we saw that the net capacitance can be represented as one connected to the ground called as CP1 and CP2, right? These are the lump parasitic capacitance, and then you have inverter here, right, followed by, let's say, some kind of filters, and then the grid. So one thing which we assume that the voltage appearing across these parasitic capacitance CP1 and CP2 does have a high frequency component, right? That was the assumption we had in the last discussion, and because it has a high frequency component, the current then flows to the earth and then goes back and sort of completes path through the circuit. So in this video, what we'll do is we'll talk about, or rather we'll derive these values of the voltage appearing across the parasitic capacitances. So let's start by drawing a little bit more detailed diagram of the inverter. So let's consider a H bridge inverter, right? This is also called as a full bridge inverter, where we have 4 switches, let's say S1, S2, S3, S4, and they are connected to the grid through these inductors. Right now, if you see, I have drawn 2 inductors. Usually, when we study about these inverters, you can just draw one inductor. So why I am drawing 2 inductors will become more clear as we go in a little bit more depth about this subject of common mode current. But just you can understand that if you put only one inductor, it will help in reducing the differential current. If you divide that inductor into 2 and put it across the 2 both phase as well as neutral, then it will restrict, or rather it will provide relatively higher impedance to the flow of common mode current also. So therefore generally it is recommended to put the inductor in both phase as well as neutral, and anyways the net resultant inductance for the differential mode behavior would be L1 plus L2, right? So nothing is lost in that sense, but there is some advantage in terms of the common mode behavior. So for the time being, let's keep it as it is, right? As we move along, we will probably be able to go in a little bit more depth of what is the advantages of keeping all the inductor on one side or distributing it half in the 2. So let's say it's there in 2 and the values are same, right? So LL, and you could have just put 1 with 2L value, which is also okay. So for the time being, let's assume this architecture on the grid side. Now, as I told you, on the substation, the neutral would be grounded. So this is the neutral, it's grounded. This is phase A. On the DC side, now we have panels which are connected, right? And to avoid the flow of the high frequency current, the differential high frequency current, we would usually also connect a DC link capacitor, right? For 2 reasons. One is to absorb the 100 Hz oscillation, right? Because the right hand side AC circuits power is oscillating at 100 Hz. We don't want the same thing to happen to the panel, and therefore to absorb that 100 Hz oscillation, we use this capacitor, and also to absorb the high frequency current that is flowing in the inverter, right? So this capacitor, because this capacitor value is large enough, usually the DC voltage is almost stiff. So to say, it may have some low frequency oscillation, but it does not have any high frequency oscillation. So if you see this VDC and if you usually plot it, right, with respect to time, you would see that it may have some low frequency, which is 100 Hertz oscillations, right? This is 1 upon 100 Hertz. But it does not have, or rather it has very small high frequency or negligible high frequency, right? And it certainly has a lot of DC component also in it. Right, and this was, let's say, let me call it as let me just name some numbers. So let me say this is capital A, this is capital B, right, and this is capital C, and then this is the ground. So what we are actually interested in is the voltage V, capital C, capital G, right? This is the value of the voltage we are really interested in. So to find this capacitor voltage VCG, which is, if you see, is nothing but the voltage across the lower capacitor, which is VCP1, right? And we can see that the voltage across the upper capacitor VCP2 from KVL is nothing but VCP1 plus VDC, right? So if we can find VCP1 or rather VCG, we can find the parasitic capacitance across both the we can find the voltage across both the parasitic capacitances. So let's start analyzing this circuit and try to find VCG. Now what I am doing is I am redrawing the circuit, right, just so as to make our analysis little bit simpler. S1, S2, S3, S4, this point is A, this point is B, L. Now instead of showing a single AC source, I am just splitting into half-half, right? Nothing changes, it's just fictitious, and let me call this point as O prime, right, where this is VG by 2 and this is also VG by 2, right? So grid voltage source, anyways they are series connected, so nothing changes, nothing is connected to the midpoint, so everything remains the same. Only for the analysis I have shown it as a series combination of two half voltage sources, and there's an inductor here L, and this is neutral which is connected to the ground. On the DC side also I'll do something similar. Instead of showing total VDC, I will show it as a split of two VDCs, VDC by 2, VDC by 2. Now assuming these capacitor is large enough, these VDC by 2s are almost constant, as we have seen. So this ripple is there but it's very small. You can also assume it to be constant or with a very low value of 100 Hertz ripple. And let me call this midpoint as O. Again, this O is not connected anywhere, so it does not change anything. It does not change the behavior of the circuit. It's only for simplifying our analysis. And this is the point C, and this is the point G, where which voltage we are interested in. Let's say this is the current which is flowing in this direction, this is the current that is returning from it, and so on. Now let me start the writing Kirchhoff's voltage law. So if you see here the inverter, it has 4 switches. Now this inverter S1, S2, S3, S4, right? So it can have different states. So what are the different states? For example, now we understand S1 and S4 would be complementary, right? And similarly S2, S3 would be complementary. So let me start with saying 0, 0, 0, 1, 1, 0, 1, 1, right? Automatically S3 is complementary to S2, so it becomes 1, 0, 1, 0, and S4 is complementary to S1, so it becomes 1, 1, 0, 0. We understand that for all of these states, voltage VAB looks something like this. So when S3, S4 are on, VAB is minus VDC. When S2, S4 are on, this is 0. When S1, S3 is on, it is again 0. And when S1, S2 is on, it is VDC. Now, if you recall in your basic power electronics course, where you might have studied about different types of modulation schemes for this inverter, there are usually two types of modulation schemes, right? One is unipolar modulation, and the other one is bipolar modulation. In unipolar modulation, for half of the cycle, right, you go between plus VD. So if I draw VAB, this is roughly how VAB looks like in unipolar modulation, right? So you switch between plus VDC and 0, right? And then for the negative half, you switch between minus VDC and 0. And these switchings within a half period is happening at switching frequency or high frequency. In bipolar modulation, on the other hand, you see there is the zero state is not used. It's always switching between plus minus plus minus plus minus. So now if you correlate from these states, you can understand that in bipolar, right, you either generate minus VDC or plus VDC. That means either this state or this state, right? You only utilize these two. And you actually switch between these two very frequently, right? Let me give some numbers to these states. Let me just randomly call it state. Although usually it's state, this is called as, the last one is called, let's say I call this one as 1, this one as state 2, and these are the two zero states, let me call it as 3 and 4, right? So usually for bipolar, you use, or rather you switch between state 1 and 2, right, at high frequency. But on the other hand, in unipolar, for example, if you are in the first half, then you would use state 1 and you can use either state 3 or 4, right? So you will be switching between 1 3 1 3 1 3 1 3 or 1 4 1 4 1 4 1 4. And in the other half, you may be switching between states 2 and again 1 out of 3 and 4, right? So this is how the unipolar versus bipolar is, right? It was a quick recap. What is a unipolar modulation? What is a bipolar modulation? So I'll come to why it is relevant to understand what is a unipolar or bipolar. For the time being, now let us continue our analysis of the above circuit for all of these four states, right? Let me start with state number 1. So I'll just quickly copy this figure, which I would want to use. So let me try once again. Okay. Let me reduce it a little bit. All right. So now if I talk about state 1, that means S1 and S2 are on. Right? So you can imagine S1 is on and S2 is on. Right? These two are on. Now I start writing Kirchhoff's voltage law equation starting from point O. Right? I have two paths to reach O prime. One path is through the positive VDC link through switch S1, and then through the inductor I can write an equation till O prime. The other is I can start from O, go through the negative side, go through S2, and then again reach till O prime. Right? So let me start writing these two equations. So if I say VO plus VDC by 2, right, then I go to the top DC link. From there I come back, and then minus LDI by dt minus Vg by 2 is equal to VO prime. Right? This is one equation. The other equation from the negative DC link is VO minus VDC by 2. You can go to point B then, plus LDI by dt, and then I can go to point N plus Vg by 2 will be VO prime. Right? This is equation number 1, equation number 2. Right? If I add equation 1 with equation 2, then you can see what you get is everything else cancels out and you get VO is equal to VO prime. That means the potential of O and the O prime is the same, right? So that was one of the reason of fictitiously representing both the sources as split, because this equality simplifies the final expression. Now what we were interested in, VCG, so I can now write what is VCG. So let me start from the ground, right? Zero potential, 0 plus VCG plus VDC by 2, right? This gives me VO, and I can similarly write an equation on the right hand side, again starting from ground. 0 plus VG by 2 gives me VO prime, right? And if I equate 3 and 4, because VO is equal to VO prime, so if I equate 3 with 4, then what I get is VCG is equal to VG minus VDC by 2. What does it mean? It means that the parasitic capacitor voltage when states S1 and S2 are, when switches S1 and S2 are on, is given by this expression. Now what if we operate in some other states, right? Let's say now we are operating in the state number 2, right? So for state number 2, that is switches S3 and S4 are on, right? So I can check from 2, you see 2, S3 and S4 are on. So if I'm operating in state 2, S3, S4 are on, and I do the same derivation, then again what I will get is VCG is equal to VG by 2 minus VDC by 2, right? I'll get the same expression, you can check it. What does it mean? It means that if you are using only state 1 and state 2, right? So if only state 1 and 2 are used, then VCG, although state 1 and 2 is switching between each other very high at a high frequency, but in both cases VCG is the same, and therefore VCG is not switching at high frequency. In fact, it is nothing but equal to VG by 2 minus VDC by 2. What it implies is that VCG does not have high frequency. When I say high frequency, I mean switching frequency or its multiple voltage components, right? This is an important observation here. It only has low frequency, which is VG by 2 and VDC kind of oscillation. So VDC is constant anyways, it does not lead to any leakage current. It has a low frequency oscillation, which is VG by 2, grid voltage divided by 2, which will have an AC component, but as we discussed, usually these parallel capacitances are small, and therefore these low frequencies, these capacitance would offer high impedance, and thus not much of a current will flow, right? It could be in the order of microampere or so. So far so good. So looks like that there is no high frequency component across the parasitic capacitance, and which is good for us, right? So now we can operate this inverter without worrying about it interfering with the protection system and so on. But as we know from literature that a unipolar modulation is better than a bipolar modulation. Why? Because in unipolar modulation you can utilize lesser value of filter elements and still achieve the same ripple current as compared to a bipolar modulation, right? This is one way of looking at it. Other way is that in unipolar modulation you can have half the switching frequency for the same performance and thus lesser losses. You can watch some of the review videos on single phase voltage source converter sine triangle modulation, and that would give you a glimpse of unipolar versus bipolar. Coming back to the capacitor voltage, what will happen for unipolar? So in unipolar, let's say we are in the positive half. So now I'm using 1 and 1 out of 3 and 4. So when I use state 1, then I have already done the derivation. I get VCG is equal to VG by 2 minus VDC by 2. What if, let's say I use state number 3. State 3 is S2 and S4 are on, right? So state 3 is S2 and S4 are on. Let me say if I use S2 and S4 on, if I use this state, then what will happen? Let us write the equation for that. Okay, maybe I need to copy this figure further. Yeah, so we are talking about state 3 where S2 and S4 were on. In that case, if I start from VO, I can write two equations, which is VO minus VDC by 2, and then I go through switch S4 to point A minus LDI by dt minus VG by 2 is equal to VO prime. And in the other equation, again I start from VO, I go to minus VDC by 2, but then I go through point B, or rather through switch S2, and therefore I write LDI by dt plus Vg by 2 gives me VO prime, right? If I now add these two equations, I can see that VO minus VDC, these terms will cancel out, is equal to VO prime, right? And now if you see, VO is not equal to VO prime, VO is minus VDC is equal to VO prime. And now I can write the voltage VCG as 0 plus VCG plus VDC by 2 gives me VO, right? And 0 plus VG by 2 gives me VO prime. If I substitute both of them into this equation, then this is the resultant thing that we get. We get VCG plus VDC by 2 minus VDC is equal to VO prime. VO prime is nothing but equal to Vg by 2. So I get VCG as Vg by 2 minus VDC by 2. If you remember, this was the same expression, plus I have an additional term which is VDC. The original expression in the other state, state 1, VCG was only equal to this, but in the state 3 it is equal to this thing. Now you understand, if you are switching between state 1 and 3 very frequently, right, at high frequency, in that case the capacitor voltage VCG will also be oscillating very frequently between these two expressions, right? And there also you will see this high frequency oscillations, right? Because you see this is also oscillating, because sometimes it is this first term plus VDC, sometimes it's only plus term. So again VCG is also oscillating, right? So now therefore if you use unipolar modulation, which is good because it could give you better efficiency and so on but then if you use unipolar modulation, then your capacitor voltage has a high frequency component, and which can force high frequency current through it, and you will have leakage current problem, right? So this is justifies what I told you before, that your parasitic capacitors may have high frequency voltages. It's not necessary, it depends on the circuit topology, right? Some of the topologies plus along with the modulation schemes may not have this problem. Some of the other topologies and along with their modulation schemes may have this problem. Here we saw a situation where it's the same circuit, but just if you switch between one of these two modulation schemes, in one of the modulation schemes this problem exists, other one it does not exist, right? So let me also, I did some basic simulation just to further strengthen this point and for you to help visualize this. So I simulated this circuit with a fixed DC source, right? And I try to observe the capacitor voltage for both unipolar as well as bipolar scenario, the parasitic capacitor voltage. So let me show you that. First let's say this one. So this here you see is a unipolar modulation, right? For the whole cycle the voltage is oscillating between plus 400 and minus 400. And in case of unipolar modulation, we saw that the parasitic capacitor voltage is Vg by 2 minus VDC by 2, right? So this is that parasitic, one of the parasitic capacitor voltage. The other one would be Vg by 2 plus Vdc by 2. So this is the other parasitic capacitor voltage, right? This is the bottom capacitor voltage, this one here, and this is the top capacitor voltage. You see there is no high frequency, it's only a DC component plus a low frequency, which might result in a very small value of current, right? Maybe in few tens of microampere or something like that, depending on the capacitance voltages, right? Or might even be less. Now if you see unipolar modulation, in unipolar modulation the voltage waveform is what we can recall, right? It switches between 400 and 0 in the positive half and minus 400 and 0 in the negative half. And you see now the parasitic capacitor voltages, right? You see a high frequency component in this voltage, right? There is this is same as the switching frequency, right? So there is a high frequency component in these voltages. Similarly for the other capacitor, there is high frequency component. This high frequency component will force a high frequency current through the parasitic capacitors, and thus forcing the leakage current. And therefore when we talk about solar inverters, we do get restricted, and it's not that any circuit topology can be used for solar inverter application, right? Leakage current being an important aspect limits the usage of some of the circuit topologies. Some of the other circuit topologies could be used, but some other topologies are not suitable for this application. That said, there are solutions, right? So even if you want to use, for example, unipolar modulation with the edge bridge, you can use it. There is some modifications in the circuit that one has to do, right? Which we'll see subsequently what are those modifications. It is possible. Obviously, there is a trade-off. You may, for example, you may have to add some additional transformer, which might increase the cost, which might increase the overall losses. But then yes, it will allow usage of even unipolar modulation schemes in the inverter, or you can do some circuit modification and then still achieve the benefits of unipolar modulation, at the same time avoid the leakage current. So what we'll do now is, this was a much simplified, if you see, much simplified analysis where we consider most of the things to be ideal, and we wrote basic Kirchhoff's voltage law and current law to show that VCG, or the parasitic capacitor voltage, has high frequency. In the next video, we'll try to generalize it a little bit, and we'll try to define something called as a common mode voltage, and we will go around and we'll talk around that common mode voltage and do an analysis in the next video.